But the question here is that is it really true that because of the network we are getting here, we are no longer able to add more flows, right? So it turns out that this is not really true, right? So this is a very crucial observation, right? So just imagine if we want to push up an additional flow that's moving towards this direction, the blue one that I'm drawing here, right? So if I'm pushing up the flow over this direction, right? So basically, let's imagine that we are pushing up 1 unit of flow for the entire blue path, right? So let's see what's going to happen, right? So let me just also redraw the whole things, right? So originally it's S to A to A. So let's just draw everything and then let's not repeat so much words here, right? So this is originally what we have so far, right? So 2 1 1 2, and then this is 1, right? So now the blue one is basically the new so now let me just use the same blue one, right? So but a little bit thicker one, so right, the blue one, right, really wants to add one more unit of flow along this path, right? So after we add one more unit of flow, right, let's see what's going to happen, right? So one more unit of flow of here, that's doable, right? That's doable because even after adding one more unit of flow, it's really 1 plus 1 is 2, right? So but if I look at the capacity network, right, the capacity is 2, right? It's sort of satisfy the constraint, right? So let's also look at the third one, the last edge from A to T, right? So this is also adding one more unit of flow, right? So this is 2, right? So again, this is not hitting the capacity limit, right? That's very central observation here is that is the flow that's moving along this edge, right? So you can sort of imagine that for the pipe that's connecting from A to B, right? So before I add this 1 unit of flow along the blue passes, right? The blue passes, right? So or before that, I have 1 unit of flow that's really moving from left to right, right? So when I really want to say that I want to push 1 unit of flow from B to A, right? So that's really just means that I sort of want to cancel out, right? Cancel out what's already existing there, right? So basically, imagine that you can really just physically imagine that if I'm pushing 1 gallon of water from A to B, at the same time I'm also pushing 1 gallon of water from B to A. What's going to happen at the end? That's going to mean that that's going to be no water needed that's moving that no water needed that needs to be moved from either A to B or from B to A, right? So let me just repeat that. If I have A and B doing things like that, 1 gallon of water from left to right and 1 gallon of water from right to left, that's effectively equivalent to that. I'm not pushing anything, right? Right. So that really just means that after I add this unit, it's really just that equals to the 1 minus 1 along this path, right? So let's see whether that's really doable, right? So at the end, what I'm going to get is it looks like a graph looks like that, right? So 1 plus 1, so now I have 2 units, right? After I cancel the 1, so for the diagonal edge, it's 1 minus 1 is 0, right? So I'm not using these diagonal ones. And for the rest of them, right, so this is S to A is 2, and A to T is 1.1, 2, and 2, right? So now you sort of see that we eventually get the optimal solution, right? So what's the moral here? The moral here is that it's even though if I look at this residual graph we thought we were able to compute, then we came to the conclusion that we cannot improve the flow anymore. But then we somehow like magically we determined that maybe we can try this blue path that's over here, right? This graph, the blue path over here, right? So the key observation is really just that if between A and B there's 1 gallon of flow that's moving from A to B, right? So literally I'm actually having this luxury of trying to push at most 1 gallon of flow from B to A, right? So I can push at most 1 gallon of flow from B to A, right? To A. So literally we can really think in this manner, because when we push 1 gallon of flow from B to A, it's really just canceling out. That's what's really happening here, right? So that means that this blue one, the blue pass we are using, it's actually a legitimate pass, right? So after I integrate this blue pass together with our existing flow, we actually managed to come up with a solution that's optimal, right? So literally what we have been doing is that in the beginning we sort of make a mistake of using the pass that's over here, right? The diagonal pass, right? This is the mistake we make, right? And actually, when we have we have this interpretation that when you are able to, we are already moving 1 gallon of flow from A to B, that really literally means that we can push 1 gallon of flow back to A, right? If we allow this type of interpretation, this really just means that we are given room to fix the problem. Fix the problem. In the sense that, right, so we at the beginning, I sort of decide to use from A to B, but somehow if we allow that kind of operation to push flow from B to A, it's really just that we are sort of reverting the wrong decision we made, right? So when we add an edge, and the edge that allows us to push 1 unit of flow from B to A, that allows us to revert one of the earlier mistakes we make, right? So by having this kind of interpretation, we actually managed to fix the problem, right? So the model is really just that the very simple building block we really need to add is that if our capacity limit is say 15, right? So these are just arbitrary number, and somehow we decided to use 10 unit of flow out of this 15. That basically means that we do have the luxury, or do have the ability, right, to really move 10 unit of flow from B to A. So that means that we need to add an edge, reverse edge, that has 5 unit of capacity, right? So we need to add edge that has 5 unit of capacity, right? So this is what we call this is how we actually fix the residual graph, right? So the residual graph is really, when I talk about the residual graph, is really just that the amount of I sort of it's too messy. This was the residual graph we were sort of trying to construct, right? So intuitively speaking, the residual graph should reflect the amount of additional flow we can push on top of the existing flow. But now the residual graph we computed just now didn't really have this kind of property, because it didn't allow us to fix any of the prior problems mistakes we make, right? The real residual graph is really needs to impose this additional gadget or trick, right? So whenever you push 10 unit of flow from left to right, you should reflect that you are able to to revert the decision, and then you will want to be able to add 10 unit of capacity. Sorry, I make a mistake. 10 unit of capacity that's moving from right to left, right? So the 10 here should match the 10 here. I make a mistake a few seconds earlier, right? So let's really just review how this little trick can help us to solve the problem, right? Let's just repeat the simple problem we were talking about just now, right? And see exactly what go through the trick we are mentioning just now, right? So let's assume that we have S, A, T, B, right? So this is 2, 2, 2, 2, 1, right? So these are the capacity of the network, right? And now what we need to do is like what we did just now, right? Just find an arbitrary path, right? So let's say we choose this pathological path, right? So after we find this path, right, let me just keep two things. One would be just the flow network we have so far, right? So S A B T, right? So the flow we have so far is 2 unit, 1 unit over from S to T, 1 unit from A to B, and 1 unit from B to T, right? So these are the flow graph. And then then let's also compute the residual graph. Residual graph, again, as I mentioned, it would be really just the amount of additional flow we can push on top of the flow graph, right? So the residual graph, right? So the first few steps of the residual graph would be similar, right? So S, A, B, T, right? So what we need to do is to copy all the edges that are already in the original graph, right? So I'm copying all the edges here, right? So these are all the edges that I'm copying. And after I copy all the edges, right? So what I need to do is to compute really just the residual capacity along these directions, right? So this is 1, 0, right? 0, and then this is 1, and this is this is 2, and this is 2 here, right? These are the first part of the residual graph, right? The second part of the residual graph will really just be that we sort of need to add some additional edges, right? So in case, right, I already used 1 unit of flow from A to B. What I need to do, let me just change the color, is to add back 1 unit here, and then say 1 unit of flow, that's 1 unit of capacity, that's back from B to A. That's going to represent the fact that we are actually able to push 1 unit of flow from B to A, right? It's not really just that it's not true that there's a route of moving from B to A in the original graph. This is not true, but because there's already 1 unit of flow that's going on, when we push up anything from B to A that's smaller than 1 unit of flow, then basically we can just cancel out the flow that's from moving from A to B, right? So similarly, for the edges that's from the BT edges, because we use 1 unit of flow, we sort of do the reverting, and then similarly we revert here, right? So all these 3 blue edges over here, right? Let me to look at this, all 3 blue edges, you really just correspond to the inverse direction of the three active flows, right? So we decide to use these 3 passes, and then what we need to do is to invert the direction of the pass, and then assign the capacity of the new pass as the current active flow, right? So at the current active flow is 1, 1, 1, so the capacity is 1, 1, 1. So at the end, our residual graph looks like that. So now let's just redraw this residual graph, and what I'm doing here is just I'm drawing things in a nicer way, that I'm not going to introduce new information here, right? So this is the residual graph I'm drawing here. S to B is 2, and the B to A is 1, and this is 2, and this is 1. This is 1, right? So the central claim here is that if we fix the residual graph in this manner, then if we are able to find a path that's connecting from S to T, that means that we are able to add new flow to the existing ones. And otherwise, if we cannot find this path like from S to T, then we should be able to find the real optimal solution. The claim is that if we fix in this way, then we should be able to find the solution. Right. So let's really just walk through the entire example again, right? So from this residual graph, let's just repeat and see whether we can find a path that's connecting between S and T, right? So let's just assume that we find a path that's from S to B, B to T, right? So let's assume this is the path we found. So now let's assume this is the path we found, and what we need to do is really to overlay this path to the original path, right? So the original path looks like that, right? Let me just redraw everything here, right? So this is S to A, A to B, B to T, right? So original path is 1, 1, 1 here, right? So now let's also overlay the new flow we found, right? So we decide to use S to B, B to T, right? So let's really just compute how much flow we can push out, right? It's really just the mean of this 2, right? Mean of this 2 gets to 1, right? So we sort of want to push 1 unit of flow that's along this red path, right? So let's do that, right? So 1 unit of flow here, and we want to push on top of existing 1 unit of flow from B to T, we want to push up 1 more unit, right? So this is 2 unit of flow, right? So let me just clean this up, right? So this is what we have so far, right? So this is current flow information, right? So let me also just write down, articulate this what we are doing here, right? So we really have 2 pieces of information that we are maintaining at the same time. The first piece is the flow information, right? So this is at high level, it is really that the flow we have found so far, right? So if you check this graph, right, so this satisfies the flow constraint, the 2 constraint, right? The first constraint would be the capacity constraint. You look at all the numbers, they actually are on all the edges, they actually are smaller than the capacity. The second constraint would be the flow conservation constraint, right? If you look at all the nodes that's besides S and T, the amount of incoming flow is the same as the amount of outgoing flow, right? So, and this would, in the flow graph, when we draw the flow graph, we actually sort of like intentionally hide the capacity information, right? So there's no capacity information associated with this graph. But on the other hand, when we draw the capacity graph, right? So these are really just all the capacity information we need in order to proceed to continue to execute our algorithm, right? In this capacity graph, actually the flow information is not directly presented, right? You can sort of infer the flow information from both the residual graph and the original graph, but for the purpose of really just presenting this idea, when we draw the residual graph, the flow information is not presented, right? So no flow information. Right, so you really just we really need to look at these two graphs collectively in order to understand the current picture and where are we at this moment, right? So now let's really just proceed and continue to update this flow graph, right? So the residual graph, right? It's A, S, T, and B, right? So a lot of edges remains untouched, right? So what we need to do is really just don't modify anything that's remained untouched, right? So the only thing we are doing here is that we add additional unit of flow along this red path, right? So that basically means that if I consider moving between edges between S and B, right? So we can move one more unit of flow because I already used 1 unit of flow and the total capacity is 2, right? But we can also use our, right, the reverse edge principle, right? That sort of means that we can also push back 1 unit of flow from B to S, right? For the reason we just discussed. Right? So similarly, right, if I look at the edges that's moving from B to T, right, I already used the 2 unit of flow and the capacity limit here. Now, if I look at the original graph, it's also 2, right? So that basically means that I can no longer push any flow from B to T, but on the other hand, I can push 2 unit of flow from T to B, right? So when, again, let me just repeat, when I push flow from T to B, that basically means that I'm trying to reverse my decision of existing flows, right? So now out of this edge, so the algorithm basically says that let's really just repeat this operation and find another path that's connecting from S to T and continue to do the update until that cannot be done anymore, right? So let's assume that this time we find a longer path, right? So S to B, B to A to T, right? So now what we need to do is really just again, like, so if I look at the longer path, right, it's S to B, B to A to T, right? So if I look at the capacity here, this is 1, and B to A it's also 1, and A to T is 2, right? So let me do the mean again. We have been doing this for multiple times. This is 1, right? That means that I want to add 1 unit of flow out of the red path, right? So and when I add 1 unit of flow here, right, I sort of do the overlay, right? So let me just change the color, right? So I want to add 1 unit of flow from S to B, B to A to T, right? 1, 1, 1, right? So now let's really do the consolidation. The consolidation start to be a bit of interesting, right? So there are some edges we never touched, right? So those are straightforward, right? So, and originally from S to B, there's already 1 unit of flow. Now we are adding 1 more unit of flow, right? So the flow here is 2, right? Now there's also 1 unit of flow that's moving from A to T, right? This is also the straightforward one, right? Now if you look at the interaction between B and A, that starts to get interesting, right? Originally, there's 1 unit of flow moving from B to A, right? That corresponds to this one, the original green one, the original red one, right? Let me just use a bolder font here, right? And now, after we do the update, we also decide to add another unit of flow that's moving from B to A, right? So if you look at what we explained, the intuition we explained just now, what's really happening is that I'm pushing out 1 unit of water from A to B and another unit of water pushing from B to A, right? So there's some consolation going out, right? So when you move 1 unit of water from A to B, another unit of water from B to A, that basically means that you don't need to move any water, right? So basically that's equivalent to delete the whole interactions, right? So basically nothing, not interaction, there's no interaction anymore between A and B, right? So now after this kind of intuition, we sort of can redraw the entire graph, right, as L18b, right? So one unit of flow moving from this direction, another unit of flow, another 2 unit of flow moving from the other direction, right? So this is the new flow graph. And after we have the new flow graph, we should really just repeat and draw the new residual graph, right? So the residual graph, as I mentioned, right? So again, like a portion of the edges remain untouched, so we don't need to do any modification. This is 2, this is 1, this is 1, and this is 1. This is actually this is not 1 anymore. Let's be careful, right? So so now I'm moving 2 unit of flow, whereas the capacity unit is also 2 unit, right? So that basically means that I'm no longer able to push any flow from S to B anymore, right? So I can write that down either as 0 or just delete the edge from S to B directly, right? But using our principle, right? So the number of flow that I can move from B to S is 2, right? So again, like so if I look at the connection between A and B, I'm not using this edge anymore, right? So the edge, original edge that's in the input graph reappears because I roll back my decision, right? So you can sort of see that, right? It's the same, right? If you look at the residual graph, right? So I have 1 unit of flow that's going from B to A. That basically means that I need to reverse again, right? Get another unit of flow that's moving from reverse direction, having the same unit, right? So this is how A to B works, right? Eventually, so we can also see that if we apply the same principle, we already use 1 unit of flow moving from A to T, right? So there's 1 unit over here, and that sort of represents that I already use half of the capacity, right? And there's also 1 unit that's really moving from T to B, right? This is sort of reverse edge we have been talking about. This reverse edge is really just the mapping this number over here, right? So just unfortunately, everything is either 1 or 2, but the way we get 1 is very different, right? So the first one from A to T is 2 minus 1. The second one is really just copying the current flow, right? So after we have that, let's really just repeat and see what would be the next ST pass, right? So if I run an ST connectivity algorithms on this pass, right, on this graph, the only remaining pass I can find is from S to A to B, right? So again, this is the capacity for both edges in the residual graph is 1. That basically means that I can only push 1 unit of flow over here, right? So after I add 1 unit of flow here, that basically means that I add 1 unit, add 1 unit. Eventually, I'm going to come up with this graph, right? So so this is 2 units moving from S to A to T, and another 2 units from S to B to T. So we sort of see that the flow we found here is already the optimum flow, right? It's already the best flow we can find, right? So let's really just do a sanity check. And we want to update this residual graph again. And then what we expect to see is that after we update the residual graph, within the residual graph, we cannot find any path that's connecting from S to T. Otherwise, we would have been able to increase the flow value on top of an optimum one, right? Which obviously means that there are some error going on in our algorithm, right? So let's make sure that after we update this residual graph, we indeed cannot reach from S to T, right? So let's draw this again as A and T and B, right? So the easiest things are, again, those edges that we didn't touch from the last iteration, right? So now we sort of we touched 2 edges, right? So the first edge would be S to A, right? So now we are already using 2 unit of flow here, right? So the capacity is also, let's say it's also 2 unit, right? So that means that from S to A, I can no longer push any more flow from S to A, but from A to S, I can push 2 unit of flow. For the same reason, I cannot push any flow from A to T, but I'm able to push 2 unit of flow from T to A, right? So if I look at this graph and as I mentioned, let's try again to run an ST connectivity algorithm, try to find a path from S to T. All of a sudden, I realized that there's actually no edges that are going out of S. That really just means that it's hopeless to find any path that's connecting from S to T, right? That really just is consistent with our expectation that we can no longer update the maximum flow, right? So the moral of the story here is that if I look at the original graph and the residual graph, right? So if the residual graph cannot update anymore, that implies in the original graph, the solution we found is also optimum, right? If it's optimum, then that also implies that we cannot update anymore, because otherwise it would be a contradiction, right? So this is really just an example showing that, right, so far our residual graph idea, right, the notion of introducing the reverse edge seems to work.